All right, continuing on with class 14. This should be video 2, I believe. Is that right? Yeah, sure. And we're going to do an example out of Sengel's book. This is example 6.8 out of his book. I do it a little slightly different, so there's a little value added going on here. So we have this underground water that's coming up through this 10 centimeter pipe. We're going to say that the 10 centimeters is the inside diameter. They're showing it as the outside diameter. And it comes up 2 meters, goes over 1 meter, and then it starts to exit at 3 meters per second. And it goes to atmosphere. And they're saying that the mass of the horizontal section here and the water inside is 12 kilograms per meter length, but it's only 1 meter, so it's 12 kilograms. The water is anchored, the pipe is anchored at the bottom on the ground in a concrete base. We're going to determine the bending moment that's acting at the base of the pipe at point A. And the required length, I'm not going to do that second part. But anyway, okay, so let's do the problem here. And first I'm going to get the area, the exit area. That's going to be right there, right? And we could call that area 2 if you want, but area 1 is going to be the same thing. And we're going to get pi over 4. And it's 10, they say 10 centimeters, so that's like 0.1 meters squared, and 7.854 e to the minus 3 meters squared. Okay. So the mass flow here, we can find from m dot equals rho AV. And I'll use what the other book has is 999. Instead of 1,000, it's very, very petty, I guess, for kilograms per cubic meter, and 7.854 e minus 3. The area and the velocity, they say, is 3. So we're going to get 23.54 kilograms per second from that. And let's see, let's get the weight of the pipe. I'll say the weight of the horizontal part. So that's what my H is saying. That's the horizontal part's the weight, and that's just the M of the horizontal part. So what do they say? 12 kilograms per meter. It's 1 meter, and acceleration of gravity. So we get 117.7 newtons. All right, so I'm going to draw an FBD and a momentum diagram of this. And in this case, it's really the control volume that we're drawing as a free body diagram. And we're going to put the forces on here. Well, we have this weight of the horizontal part. We also have the weight of the vertical part, which we don't really care about, but we're going to do it anyway. We're going to have a reaction force here. We'll call that RAY because it's at A. And there's also going to be a reaction moment. We don't know what direction necessarily this is going to be. So I'm going to go, default is counterclockwise. And if we decided, let's see, declare that to be X and Y, therefore this is the moment at A about the Z axis. And over here on the momentum diagram, oh, by the way, I forgot a force we need to include on here if we're going to be 100% accurate in our depiction. I guess I could kind of put it right in there, but I kind of want to give myself a little bit of room and put it right there. Okay, so I want to put like a little pressure distribution kind of symbol right in there. I call that RAY right here. I'm going to go P1 times A1, all right? That's not going to matter for us because we're going to take the sum of the moments about this point right there. And so that's going to be passing through the point about which we're taking it. But I think it's a really good idea when you're making an FBD that you are inclusive of all the forces that are taking place, because you could get burned later on in life when you go to make something much more complicated. All right, so let's be inclusive of all the things that we would want. Here's M dot and V1 passing through right here, and then we're going to have M dot V2 passing right through there. And we note that this, what did I decide to say? Okay. Sure, I see what I did. Okay. So anyway, This is, okay, the sign from this is based on the equation. Is that true? Yes, I think so. Yeah. Well, one thing, okay, this is, so technically the sign is actually going to be decided from the direction of the velocity, right? So the velocity, yeah, is going to be causing a moment, right? So this is really, we should be doing the r cross this velocity and the direction that this is going based on that. I think that's right. Yes. Okay. So anyway, let's take the sum of the moments about A. It's going to be equal to the sum of the, and we'll write out the equation that we've been given right here. V out, and then the sum of R m dot V, and this is in. We can see though that this is not the R that we should be using for the in. Let's go ahead and do this diet over here. So I am going to declare, yeah, okay. That's how I'm going to do it, right? So let me say that counterclockwise is positive. So we're going to have MAZ is our reaction. That's the thing we want to try to find. Here is going to be clockwise right here, so it's going to be negative, and I just went ahead and put numbers in there. 117.7, and that's going to be times 0.5, because that's the length right here, so that's that distance right in there. And then that's going to be equal to m dot v right here. But that is coming in the clockwise direction. So that's actually going to be, create that to be negative. So we're going to go, and the r here is the distance right to there, right? So we know that's going to be 2 meters from here. I think I got that correct, yes. So, and then the m dot, we were told, well, I calculated through 23.54. And then the v is that 3 meters per second. And once again, that negative is because of the direction in which this thing is moving, right? So this velocity and dotted across, I guess, against this r right here is going to make a negative direction. And yeah, so and then this part, there's nothing coming in, right? So the inlet of this, well, there's something coming in, but it's coming through here, so the r is actually 0 right there. So our MAZ that we get out of this thing is actually going to be a negative value, even though we chose as default as being positive. And you might think, well, that's counterintuitive in terms of the way we think this is going to go, right? We would think, oh, this is going to thrust this thing to try to push it back that way. So you're going to think that it's going to be a moment that's counterclockwise. But remember, in FBD, we're drawing what the reaction is, right? So that yes, this would be imposing a counterclockwise thrust, but the reaction to this is actually going to be clockwise, right? To try to hold it in place is what the reaction is. So that's an important distinction right here. So we could say, so this is what the ground is doing the moment that the ground is doing onto the pipe, right? And so let's see, yeah, I said that the right way. So we can say that it's 82.39 Newton meters clockwise. But let's, I think I want to add to this. Let's get this stress here at this location, because you've taken mechanics and materials, and you're taking the elements of mechanical design, the machine design class. So let's find what the stress is in the pipe. There's going to be compression here on that side, and let's over here. Compression here on this side, and tension over on that side. So it's going to be plus or minus, and we know it's going to be MC over I. So we want to see what the value of this is going to be. And so the moment that's going to be placed on there is the 82.39 The C is going to be 1/2 the diameter. Now, let me also go to a side that this is pipe, right? And pipes come in standard sizes. And 10 centimeters is 100 millimeters, which is almost 4 inches, or right there around 4 inches. So, and if you were to look up for a standard pipe, the most standard pipe is Schedule 40, and this is in US standards. And if you take a look at the Schedule 40, they have an outside diameter of 114 millimeters and an inside diameter that's pretty close to being 100 centimeters. So the OD is 114 millimeters. That's a wall thickness of close to 6 millimeters, right? So so if you were to subtract out that, there's like 100 inside diameter is like 102 millimeters. 1 sec. Okay, cool. So half the pipe. Okay, so the let's just go to the outside diameter is going to be 0.114. I think I got that wrong actually written on here. 0.144 divided by 2, and then the moment of inertia, pi over 64, and then take the 0.114 of fourth, and then minus out the inside diameter, which should be 0.14, or pretty close to it. And I got the number wrong here on my sheet, so I have to calculate this live. Let's see, 83 point, what is that, 3939 times 0.114 divided by 2 times, and then take 0.114, raise it to the fourth, and then 0.1, raise it to the fourth, and subtract them, and then I can go ahead and divide that out. Yeah, I can divide that out, and then take divide by pi, and then multiply by 64. And we get just a little bit different from what I had before. 1.40, call it 6, e to the 6, and these are Newton meters per second, so that's a million. So that goes 1.41 megapascals. So that's going to be what the stress on the pipe is. Because this thing is pushing it out way, it's going to try to push the pipe over there. So we're going to have tension right here, and going to have compression right there of this amount right here. So there we go. It's sort of a practical application of this momentum, angular momentum causing a moment. The end.